So is it better now? Shall I restart or no? No? Yeah. So I was talking. Yeah, I was saying that when I moved to the eventual consistent, I brought with me the sense of fault tolerance, and I've noticed that eventual consistent systems actually they trade consistency for availability, and then they almost run in the wild, and they care about just the what we call crash recovery model. Or and I just wanted to design some solution for these systems. And I thought that because I've worked on both areas, so it might be a good trade-off to design that thing. And I'm going to propose probably this one. So this was presented in a URSUS pop-up workshop. I'm going to give an overview of that system. But a friend of us, an expert in both areas as well, have seen that paper, and this led to a long discussion with him. So the discussion was, like, the end of the discussion was, like, there are no BFT fans anymore. So just like, you know, when you have a good work and you invested time on that and someone says that, you just throw your work away. So I just like, he boxed me in the corner, and I wanted a killer answer. Like, my answer was like, at least Leslie Lamport is still living. So if you know that Leslie Lamport is the founder of Byzantine Fault Tolerance, and he's defined this in his paper on Byzantine generals problem in the 1980s. So, but then I think that then I realized that this was a bad answer. Actually, it was like kind of surrender, like, because he is actually proposed the Byzantine generals problem, and he's probably will be the first sponsor of that language, of that problem. On the other hand, add to the complexity of Byzantine Fault Tolerance, actually Lamport also is the author of Time Clocks, and this paper that's considered the seminal paper of distributed systems, and it's very complex. And the Paxos paper, which is also very complex, so he started working on that in 1990, and after 8 years, the people just grasped the idea, and even Nancy Lynch proposed that, yeah, that's very complex, and it's worth another paper, and then he published another paper, which is Paxos Made Simpler in 2000. So even just the kind of naive application, like it's document editing, he made that complex. So Leslie Lamport is a bad example to measure on that. So, and then I realized that this is not a good answer, and I tried to analyze what was the reason behind why BFT is not being adopted in the industry. So I had some thoughts that I would like to share with you, along with my design, and I would like to get your feedback. So this work was done with my student Hussam Yakteen and Carlos Baquero, who works on conflict-free replicated data types, if you know him, and within a project, edge computing project called Lightcone, which we will continue developing CRDTs there if you want to follow. So in this talk, I'm gonna give a brief background on BFT and eventual consistency, and what are the problems with Byzantines in this kind of systems, and what is my design that I'm proposing, the trade-off design, and a ramp up. And throughout this talk, I'll give my highlights on why BFT is not being adopted in the industry. So let's start with this, and sorry for the harsh probable image. So this kind of story that used to happen in the 19th century, like whenever someone dies and you ask the physician, and he says that it happened, and currently we don't accept this kind of argument in this century, because it should be something scientific, like it's a brain stroke, it's heart failure, it's something like cancer. And this analogy also goes for the computer systems. So you often see like The system is down. The system is unreachable at the moment. We are sorry about that. There was a leakage in the system. That's embarrassing. An unexpected failure caused something. And these are also no longer accepted arguments in this century. So what I want to say that here, you probably might have expected that to bring you, like compile a list of Byzantine failures that happened, and then I motivate my work. So yeah, this is a list of failures actually in real systems, and that's why it's important to talk about Byzantine fault tolerance. But I want to go beyond that, actually. So I think that there is some barrier in Byzantine fault tolerance and between Byzantine fault tolerance research community and the industry, actually. And if you notice that from the proportion of the industrial people here who know about Byzantine fault tolerance, so it's 10%. So the message, the first message that I want to convey, that we couldn't figure out if there are Byzantine faults, or where are they, and or how do they behave if we don't have access to the systems. So we need your help from industry, and you have to be more educated about Byzantine fault tolerance. So you find problems and we solve them. Just your phrase, it looks a very bad like phrase, like you do bugs and we fix them. So, but you have to discover or describe what happened. And if you don't know about Byzantine fault tolerance or even the definition and how do they behave, so you couldn't help us. Okay, so my first message is that I think that developers, they need to be more educated about this kind of failure. So then let me start with the overview or the background of Byzantine fault tolerance. So the Byzantine fault tolerance model is the strongest model in the fault class. So, and it's the strongest because the nodes actually behave arbitrarily. So you couldn't expect how do they behave. So just a couple of different types of errors, like it could induce errors, it could induce bugs, it could empty a registry, delete a memory, okay? Another thing is it could behave maliciously, or it may collude with other nodes to do something like even errors or bugs, or could even behave correctly. So this is also a challenge. I will come to this later on. So actually the main approach that I'm interested in here is something called state machine replication, in which your system, like the cluster, a couple of servers, they work as if they are a single deterministic machine. With the same input, it should give the same output. And it works with the majority consensus. So if you know Paxos, it's a kind of close, or it's a quorum system actually. And in this system, the write quorum and the read quorum should intersect in a non-Byzantine fault. So it's not enough to have one intersection. The intersection should be non-Byzantine, okay? Because a Byzantine replica could lie. Okay, so you couldn't rely on the result. And it's known that you need, to tolerate one fault, F faults, you need 3 F plus 1 nodes. It means to tolerate one faulty server, you need 4 servers in the cluster. Okay, so and one of the most known probably, and it's the first practical protocol, is PBFT, which was built in the paper was published in 2000 by Castro and Liskov. So the main challenges in this system are, so we have, it's impossible to distinguish between a Byzantine replica and a slow replica. So here you're going to think about the availability. So when do you consider that you have a response or not? How much would you wait or not in asynchronous model? The second challenge is the independence of failures. So nodes must be diverse, but they also must be deterministic. And it's a kind of controversy. Like you need all the machines to be deterministic, but they have to internally be different. And here it might be challenging because you need different software and different hardware installed in the same cluster, and they should work together as if they are one machine. And also, it's impossible to distinguish between well-behaving Byzantine nodes and correct nodes. And I will come to this later to show you. It's mainly on the client side, you will see. So I come to the second highlight, which is Byzantine fault tolerance may be costly. So you need additional servers. Actually, to build your system, you need a cluster of 4 servers to tolerate only one Byzantine server. And I had before a talk with the OpenLDB community. It was trying to integrate this in OpenLDAP. And when they discovered that we need 4 servers, they got, are you crazy? And they've escaped. So also there should be hardware diversity. Otherwise, all the servers will fail at the same time. And a kind of inversion programming, like you need the same system. It's better to be implemented by several groups, several developers, probably in several languages with several libraries, and that's very costly. So this is the second highlight, probably. So now coming to the eventual consistency, probably I'm expecting that you are more familiar with this model. So in this model, you trade consistency for high availability. You care about AP in the CAP theorem, if you know the CAP theorem, which means you care about availability under partition, network partitions. So the model here, when you have, for example, here, you serve the requests of the clients on each replica without doing any synchronization with the other. So it's super fast because you are immediately giving the clients the answer, and you have to accept the application. It has to tolerate that it will read in the past. Okay, so it wouldn't read probably the last version that's written, and then each replica then propagates the updates to other replicas. And of course, since you are doing updates at the same time, there will be some conflicts, like a kind of, if you are using GitHub or something. Okay, so you have to fix this later. So fixing this, you have to fix it manually, or there are new solutions like CRDTs, conflict-free replicated data types, that are mathematical-based solutions that can do conflict resolution by themselves. So this is kind of the eventual consistency model, and its derivatives like causal consistency and all the relaxed consistency models. So what happens if there is some Byzantine fault in these systems? Actually, what happens is that a lot of problems. I'm going to focus on 2 of them. So one of them is on the client side, you will give the clients wrong values. So this wouldn't happen in another model, like the non-Byzantine model. You wouldn't expect that. But if the server is compromised, like it's malicious or it has some bug for some reason, it's going to give wrong results to the client side, to the clients. On the server side, you should be expecting eventual consistency, but your system will never converge. Okay? So, and this was because different servers are executing different operations. So as long as these operations are commutative, or you have a way to reconcile them, it's okay. But here you have a server that is actually changing the values. So you will never converge. It will change the values. Just let me give you a practical example. Like this is a simple replica of a counter that's replicated on 2 replicas. One of them is Byzantine, which is B, replica B. So the state of the counter is 3, started with 3 in both of them. And then you have an increment operation A on the first, and then the state becomes 4, which is correct. A decrement on replica B should lead to the value 2, but because it's Byzantine, it's working as arbitrary, so the value is now 7. Then when you coordinate the servers, when you synchronize and you send the operations to each other, you propagate the operations, you will end up with different values at the end. So on replica A, we'll have value 3, and on replica B, we'll have value 8. And hence, your system is divergent. Okay? So this kind of fault on the server side. On the client side, of course, you have got the value s equals 8, which is wrong. Okay? So why don't just use BFT to prevent this, to allow for convergence? And this is the known story of the debate between strong consistency and eventual consistency. Because in BFT embraces strong consistency. So you have total order, you have synchronization, you have you're gonna block the clients, and you can't afford this in eventual consistency. So my third highlight is the bad timing of BFT. So actually, the first practical Byzantine Fault Tolerance protocol appeared around 2000. And this was the exact date of the CAP theorem. And so there was probably, most of the systems are becoming like scalable, and high availability is a major concern. So all the focus went there to the CAP. And there wasn't so much interest in Byzantine fault tolerance, probably. So this, I think that this is one of the other reasons as well. So, and this is probably one of the reasons why I left BFT to eventual consistency, to work on eventual consistency as well. So what will be the approach? What will the approach to build such a system? Like, how could we do if Byzantine fault tolerance is strong consistent and eventual consistency is not? So how could I come up with a trade-off? So my work is actually to add some Byzantine fault tolerance feature to eventual consistency. And then my protocol would look like this. So add to the complexity of Byzantine fault tolerance the complexity of eventual consistency. And so that would be a crazy system. And of course, this is not what I'm gonna present. And we have already spotted some complaints from even the research community, like this paper, which is called The Saddest Moment. And the saddest moment, this is a research from Microsoft. The saddest moment is when he attends a conference where a BFT protocol is being presented. And I hope he is not here. So this is becoming frustrating even for the research community. So, and also if you need something that's more practical, some people actually have tried that. So there is this paper on Byzantine fault tolerance for services with commutative operations. So even they've tried to integrate this BFT stuff in the eventual consistency system themselves, and they figured out this. The optimization mechanisms outlined in section C, which is about the technical details, are not yet implemented due to their complexity. And this is expected because even Byzantine fault tolerance by itself is complex. So integrating it with EC will be like additional complexity. And this brings me to the highlight 4, which is BFT is really complex, actually. So I'm not sure, I just put, but maybe not that much, because probably because I've worked on Byzantine fault tolerance, I've noticed that I've got more familiar with that. But I often compare that to Paxos, and I think that Paxos is even more complex than BFT protocols. On the other hand, if BFT is complex, why just not use it in an intelligent way? So, and here comes my proposal. So here is an eventual consistent system. I have 4 servers, and the propagation is being done by a reliable broadcast between them. And each one has a log. The green light is a log. And you notice that you have different log for each one, because everyone is executing client's requests on the fly, okay? So you expect different operations, but eventually they're gonna propagate these updates to each other. And then what do? I need to just add a plugin, which is a Byzantine Fault Tolerance proxy for each one. And this proxy communicates with a BFT cluster. This BFT cluster is a BFT protocol running on 4 servers, say, if you have 4 servers that are not integrated in the service itself. But just the proxies, they issue requests to this cluster and they get response. So if you notice here that I have that the BFT runs at a consistent offset. So here I have a problem. So I've said that we have different logs for every server. So now if I've sent these logs to the Byzantine cluster, BFT cluster, so it wouldn't be matching. So the values wouldn't be matching because they are clearly different. So I can't do this matching. It will not approve the request, the BFT cluster. So how could I need something that is consistent on all of these replicas. So here you have to think about the consistent offset. So for all these logs, since they are propagating the updates across themselves, so at some point I will find in my history, in my log, a consistent offset for these operations. A consistent offset means that you have all the operations executed on all the replicas. But it doesn't mean that the same order should be there, because it's eventually consistent. Like the order might differ. But since we have like ways to reconcile this, probably using CRDTs, or if the operations are commutative, so it's okay for me. But what I want to guarantee that this yellow color is all the operations on all these replicas, and it's already been executed. So now these yellow colors should be the same if the service is correct, if none of the servers is Byzantine. So what do? I just, in the background, I look at the tail of the log, and just I push it to the BFT cluster, and I get the answer whether they are matching or not. So you can see that BFT runs on a consistent offset of the critical path. So if you see the upper side, the system is just working like eventual consistency. Okay, so there's no blocking by the BFT cluster, but you are just verifying the consistent offset of these logs. So this we say that this is an accountable model. So like, for example, here you would expect from the client, for example, to see some errors because you are not verifying the head of the log. You are verifying the offset, which is in the background. But in an accountable model, the client issues requests to one replica, and then the replica immediately replies with the last certificate. So what's the certificate? The certificate is a proof of correctness, which says that this consistent offset is actually matching on all replicas. Okay? So how this proceeds? So as long as the client is receiving an up-to-date certificate from the BFT cluster, it knows that at some point in the history, the service is working well. Okay? So this means that the client should have some tolerance for faults, at least for example, let's say you have a metric K. So a client could tolerate, for example, 1,000 requests without being verified by the BFT cluster. Okay, so if it has this tolerance, so as long as it's receiving new certificates, it's okay for us. If not, or if the certificate is bad, it needs to roll back. The client needs to roll back. And in a kind of the client here could be a cache server or a proxy or something. It might not be the end user. Okay, so it might have some rollbacks. Or you can just even notify the client So even without rolling back, at least you've notified the client that there was some error. So I think this is the best that can be done on this front. How could you keep high availability of the system, but also verify it using Byzantine fault tolerance? So this design actually, I think that is very practical because it's modular, right? And it gets all the nice properties of modularity, actually. So among these, for example, you can use a BFT solution off the shelf. So I don't want you to fiddle with Byzantine fault tolerance protocols. Which protocol? You can use BBFT, you can use blockchains, you can anything. So just regardless of this part, you can just use something off the shelf as long as it has a clear API that you can fire your requests across. The second thing is it's easy to test and maintain. And this is a property of modularity, actually. You can just even turn off that service using a configuration metric and test this system aside and the other system aside. Because simply this is running in the background. So it's not critical, very critical to change things or stop things. And then you have this safe integration because you're gonna keep your current system running. So you don't need to change your code. You just need this plugin for the proxy. And you just can, for example, test the BFT cluster and then you publish it. And finally, there's a nice thing, which is there's a spectrum between spectrum of solutions for BFT and eventual consistency options. So as I've said, that depending on the number of requests that the client could tolerate without being certified by the cluster, you can have, for example, if you don't tolerate any request, like k equals 0, it means that you are running on the BFT cluster exactly, so as if you are running a BFT protocol. On the other hand, if you have k equals infinity, it means that you tolerate everything, which exactly what is eventual consistency now. So your eventual consistency now doesn't care about Byzantine fault tolerance, which is k equals infinity. It means that whatever the replies I'm getting, I don't want to certify them. I don't want to verify them across the network. And this means that you have the spectrum between these. And probably, for example, it depends on the application and the servers. Like, I might think, like, for example, k equals 1,000 might be a good tolerable. So depending on so it's roughly depends on the service actually and the load. So, but you have a big spectrum in this. So in this approach, so why do we use this approach? Because you need to care about, if you care about consistency, in eventual consistency, so you have to use it. Because as I've shown that if you have a single Byzantine server or even client, so you will end up with a wrong service. You will not have conversions, which is consistency in the eventual consistency. Also, you might want to achieve this consistency by using PBFT itself, but that's useless because you can't give up availability. So you need some kind of trade-off between them. So also you need to care about your legacy system. So it's not practical at all to go and change your system with integrating it with Byzantine fault tolerance, and that would be very risky. So in this way, you just keep your system running and you just do it as a plugin for your system. And also, if you care about your customers, you can give them the different options, like among your clients who wants to use like eventual consistency, he can set that parameter of k equals infinity, and it's done. He is still using eventual consistency considered. And then, if your client, another client, is very conservative, then he just can put k equals 0 and can be using Byzantine fault tolerance itself and the spectrum that I've just explained. So also there is a cost for this. There are trade-offs actually. So here I'm assuming that the client should tolerate some faulty history. So, and I'm not sure if this is realistic or not, but I just compare, like, even now in the AP systems, you trade consistency for availability. And actually consistency is a correctness property. And fault tolerance also, to tolerate fault, is a correctness property. This is about integrity. So it's a correctness property. So probably it's similar, like, yeah, let's trade fault tolerance for high availability. But at least eventually, in the case of eventual consistency, you will be consistent. And in our case, eventually, you will verify your system across the Byzantine fault tolerance. And so this is the first challenge, actually. But as I've said, that the client could be not the end user. It could be like cache server or proxy servers, or it's within the same cluster. So it's client to another service. So also there is a trade-off of the BFT assumptions that we have seen already. So you will need more servers. You will need to use cryptography and this kind of stuff. You will need to have diversity in your system. Like, as much as your system is failing independently, it's better in this kind of systems. Okay, and that's costly actually. But probably recently, I think that every system or microservice or something has different implementations, good implementations in different languages. So it's getting easier. So, and at the end, the clients are not allowed to talk to multiple replicas at once in my solution. And this brings me to that point where the Byzantine nodes can actually act in a correct way. So, and this was also confusing because now, for example, in the eventual consistency model, like, clients can send requests to different servers. So what if you send, like, if you have on a set, add an item A, add A, and then you fire this request across different servers as well, add A, add A, add A. So from the perspective of eventual consistency, it's a different request. So it's not an error, it's a different request. And if you see that from the perspective of Byzantine fault tolerance, it has nothing to do with the system. What BFT cares about is consistency, actually. If the node is Byzantine and it's acting correctly, that's fine. Okay, so that's the problem. So, but how to stop that on the eventual system? Because this is probably a problem with semantics. Like, you should not allow clients to fire the same requests across replicas, different replicas. Thank you. And that's why currently the solution for us is just like every client has to stick with one server. And this makes sense in the eventual consistency model because often, like, clients access the closest server to them. And I think, like, in general, the solution for this is actually, it's not like Byzantine fault tolerance for this problem. It's like how to figure out the patterns of clients that are attacking. Okay, and this has something to do with machine learning or something like this. So I come here to the fifth highlight, which is this last point that I've just discussed, that actually there are limitations in Byzantine fault tolerance, and Byzantine fault tolerance is not a panacea, so it will not solve this problem, exact problem, when the Byzantine nodes are behaving well. So even if you have a Byzantine server who is behaving well, you will never know. And even you don't care. So in the Byzantine fault tolerant mindset, you don't care about that. Okay? So just final takeaways, like here in my system, I have like the eventual consistency community meets the Byzantine fault tolerant community. Why? Because you're gonna stay highly available and you will give the option to the client to be secure or not. Okay, so it has this flexibility. And you also have to focus, if you are an eventual consistency engineer, you just focus on eventual consistency and just leave the BFT experts do their stuff. And the opposite way is also the same. So BFT experts have to focus on their work. And you can just compose these systems. And then you never compromise your running system because it's just a plug-in. Just plug in BFT and you go. And then here I ramp up these 5 highlights here in front of you. So I would like to have your feedback if I'm missing some of them, or why do you think that BFT is not widely adopted in the industry? And if you have any questions, I'm happy to answer. Thank you.
So you mentioned that the eventually consistent system is not impacted as long as the BFT stays in the background.
Yep.
But eventually, isn't it a problem that the BFT system won't be able to catch up with the offsets, will stay far behind with the eventually consistent system, and eventually you run out of log space and you have to do something which might introduce some blocking somewhere in the system, right?
So the blocking depends on the configuration of the client. So it turns, you have to think about how many operations or what's the size of the log that the client accepts without being verified. But at some point, if there is a parameter and it's met, so the client has to be blocked. And then you have to take a decision whether you stop or you make a request to change that number, for example. But simply putting this to infinity, it's as if you accept everything. You accept Byzantine faults. And that's why this is a trade-off solution. So I'm not allowing you to do what you have already been doing on eventual consistency, on the pure eventual consistency model, which is just you can accept anything that's coming. Okay, so what I'm saying is that your model, your application should accept at least a number of operations that are not being verified, okay? But progressively, the history of your log is being verified. So progressively, it's being verified. So you always know that the last operation, number 1000, is verified, okay? So just later, you know later that these operations, historical operations, were correct, okay? And that's why you need to roll back, actually. If you figured out that some certificate in the past was wrong, it means that some operation was executed wrong on that replica. It was Byzantine, and you have to change that. That's why you need to roll back. And yes, you have to block the client in this case. And that's the trade-off, or you just use eventual consistency. But what I'm saying is that your system will not be consistent eventually. If you have a single Byzantine fault, your system won't be consistent, and you have to fiddle with the solution yourself. You change the database values and this kind of stuff to fix that.
Yes. If you have a high throughput system, can the verification keep up with the load? Or if you have a lot of requests incoming in your eventually consistent system, if the BFT cannot keep up with the verification?
I think the question is the load balance. So even if you have a great load on the system, as long as there is kind of load balance propagation between the replicas, so you will have this offset will increase quickly, and then you are verifying quickly. So verifying across the BFT cluster is costly, but it's 1 second or something. So it's not that big number, okay? But the problem is when you have much load on one server and not on the others. So you will have difference in the offset, and the clients who are firing requests on that replica, quick replica, will have to wait or will have to be blocked. Okay. So I think we have to think about this also to find like what could we do in this case.
Yeah.
Thank you for your question.
Yeah.
Yeah.
And another question, did I understand correctly that for this system to work correctly, that also your eventually consistent services need different implementations across different languages, different libraries?
Yeah, well, this is...
because that, for the industry, that gets very, very costly.
Yeah, that's correct. And that's actually the assumption for Byzantine fault tolerance and probably for other systems like even like Paxos or something. Mm-hmm. You will need to have some diversity. Otherwise, probably like some hardware, if you have a bug in some hardware, all the servers will be down at the same time.
Yeah.
So here we are talking about software, not only hardware. So also software, it's better to be different. So in some cases, there might be some fault that's not related to the implementation itself. So one server might fail, but the other not. Or you would have a malicious attack, an attack on some server, but on the others not. But in multiple cases, if something is related to the implementation or the libraries that you are using, it's likely that they fail together. And that's actually an assumption for...
So then it basically becomes an issue of what kind of errors can you catch and what kind of errors do you accept? Do you accept the software errors, but do you want to catch the hardware errors or something like that?
So actually, when we say that a Byzantine replica, we mean everything. So even the network. So the behavior on the network, the behavior on the memory, on the CPU, on the libraries, on everything. So that's the kind of diversity that we want. You don't need this kind of diversity probably in systems like Paxos because you assume that the replies are correct. So what could happen, what's the wrong thing that could happen is just turn off the server, or it's inaccessible, or you don't have the link network. So because it will be just like crash fault, like you don't have access to this server. So it's simple. But in our case, no, you have access, but it's giving wrong values. How to detect that? You have to have witnesses, other replicas that are applying, and if they are all coming from the same developer group of development, there's likely a chance to have this same error, and you will not figure out that error. Yeah, so this is a fundamental assumption in Byzantine fault tolerance. But I think that recently we are seeing a lot of implementations for every important service actually in different languages. So this might not be a barrier. And another thing to add is faults are costly. So what do you do when you have failure? So you are paying the cost when the failure happens. So why not just paying that before? So I think it makes sense.
Thank you.
You're welcome.
So maybe you can...
I can take questions offline. Yeah. Thank you.